Okay, so this is an introductory talk for the session on group actions on hyperbolic spaces. I want to thank the organizers of NCNGT for putting together a really great, thoughtful conference. So what I want to do today is give an introduction to um, some of the tools we use to work with hyperbolic metric spaces and um, kind of survey some of the results that you can use hyperbolic metric spaces to prove about lots of different types of groups. So the message I want to get across today is that hyperbolic metric spaces are really great tools for understanding finitely generated groups from many different perspectives. So what kind of different perspectives can we take? So first of all, we could take an algebraic perspective, maybe thinking from the perspective of someone taking an undergrad abstract algebra class. So in an undergrad abstract algebra class, we might wonder about subgroups of our fixed finitely generated group. We might try to understand normal subgroups, quotients of the group, homomorphisms to and from the group, and maybe extensions of the group. Another perspective we'll see today, which I'll do a bit to explain, is a geometric perspective. So we can actually think of groups themselves as geometric objects. And, after we've started thinking about them as geometric objects, we can start to ask basic questions about their geometric properties, like volume growth. So if you have balls in your space and you allow the radius to grow, how does the volume of the ball grow with the radius? You can ask about distortion of subgroups. So is the geometry of a subgroup nicely reflected in the geometry of the group containing it, or is the group kind of distorted, kind of wrapped up in some way? You can ask about dimension of groups. You can ask about some notion of boundaries. And generally, you want to understand all kinds of different subspaces. And in particular, a very interesting class of subspaces would be the Euclidean subspaces. You can also take a computational perspective. So trying to understand how to write algorithms to tell you things about your group. And in order to do this, you need to solve some basic computational problems like the word problem, the conjugacy problem, and the isomorphism problem. And finally, you might take a dynamical or probabilistic perspective. So on the probability side, maybe you want to understand random walks. So if you start at a point in your group and move in random directions, one step at a time, what does your trajectory look like on average? You can try to understand random groups. So what if you take like a random presentation of a finitely presented group, what properties do you expect that group to have? And finally, you might want to understand actions of your group on measure spaces. So thinking about this leads to the notion of measure equivalence, for example. Okay, so before we get into all that, let's just start simple by defining hyperbolic metric spaces. So first of all, these are going to be geodesic metric spaces. So what is a geodesic metric space? So a geodesic metric space is one in which you have geodesics joining any pair of points. So for any x, y, and x, there exists a path P with endpoints x and y and length equal to the distance between x and y. So this is just a length minimizing path between its endpoints, and a geodesic metric space has one such thing for any pair of points. So I'll denote a geodesic by bracket xy. This is a little bit of an abusive notation because such a thing is not necessarily uniquely determined by x and y. In other words, there may be many different geodesics between the same pair of points, but whenever you see bracket xy, you should just substitute in any geodesic between the 2 points, and the property should hold. So we say that the geodesic metric space X is delta hyperbolic if the following condition holds. So for all triples X, Y, and Z and X, we have the following inclusion. So any geodesic from X to Z is contained in the delta neighborhood of any geodesic from X to Y, union with any geodesic from Y to Z. So this definition was first written down, and the properties of hyperbolic metric spaces were really first codified by Gromov, but similar ideas had been kind of kicking around for a while. So Cannon had kind of earlier studied some similar ideas. So what is this definition saying geometrically? So geometrically, it's saying something about triangles. So X, Y, and Z will span a triangle. You just take a geodesic between any pair of these 3 points. That gives you a triangle. And hyperbolicity is saying that this triangle will curve in on itself. So you have these 2 little bean-shaped regions. What are these representing? So these are delta neighborhoods of 2 of the sides of the triangle. And what you see is that since the triangle curves in on itself, this side from X to Z is contained in the union of these 2 delta neighborhoods. So hyperbolicity is really capturing the property of triangles curving in on themselves. So what are some examples? So the easiest example to get your hands on would be trees in the sense of graph theory. So what's a geodesic in a tree? Well, between any pair of points, there's just a unique path between the points, which doesn't backtrack. So it never at any point turns around and starts going back the way it just started going. So there's a unique path without backtracking. That's geodesic. What do geodesic triangles look like? Well, here they are. So you just look at these geodesics, and when you stick all 3 of them together, you just get a tripod. So triangles are tripods, and this is actually going to be a 0 hyperbolic metric space because any one side of this tripod is actually contained in the union of the other 2 sides. So this is a 0 hyperbolic metric space. That's about as hyperbolic as you can get. So you kind of want to think of smaller delta as being more hyperbolic in some sense. The other classic example would be n-dimensional hyperbolic space. And this is actually a bit of an exercise to show that this is hyperbolic. So maybe you've seen the Poincare disk models. Well, triangles look pretty curvy in this space, so you would expect it to be hyperbolic. But let's actually run through this exercise together. So why is this hyperbolic? Well, one way to see this is by using this really beautiful formula for the area of a triangle. So you take some random geodesic triangle T, and it has 3 angles, alpha, beta, and gamma. And then the beautiful formula for the area is pi minus alpha minus beta minus gamma. So in particular, the sum of the angles is less than pi, and the area is less than pi as well. So there's actually a bound on the area of any triangle, which is very weird if you're coming from thinking about Euclidean spaces. So what do we learn from this? Well, there exists a bound R naught on the radius of any ball inside T. Okay, so the volume of a ball, the area of a ball of radius R naught, of radius R, is going to grow as the radius R grows. Eventually, if the radius is big enough, the area is going to be bigger than pi. So you could calculate very explicitly a bound R naught on the radius of this ball. I'm not going to do that, but I'll leave that as an exercise. So what else do we learn from this? Well, just rephrasing this condition in a different way, this tells us every point of T is distance at most R naught from some side. And why does this tell us that our space is hyperbolic? Well, let's go back to the definition. So we need to pick one side of this triangle and show that it's uniformly close to the union of the other two sides. So let's pick this side, and then we have to pick some point on this side and say it's uniformly close to one of the other two sides. So, okay, let's pick a point. And now we can just imagine traveling orthogonally away from the side of the triangle until we hit one of the other two sides. And as we do this, we may move a distance R naught without hitting one of the other two sides. If that happens, what do we learn? Well, we just go a little bit further than R naught, and we know we're at most R naught from some side of the triangle, but we're actually distance greater than R naught from the side we started on. So we're distance at most R naught from either this side or this side. So our original point on our original side is distance at most 2 R naught from one of the other two sides. So this metric space is 2 R naught hyperbolic. And again, you can calculate R naught very explicitly if you like. Okay, so that's hyperbolicity for metric spaces. What about groups? So a group G is hyperbolic if it acts properly discontinuously and co-compactly on a hyperbolic metric space. So what's going on in this definition? So proper discontinuity, this is a property familiar from an algebraic topology class, probably. Co-compactly means that the quotient of this hyperbolic metric space by the group action is compact. So this definition is probably a little opaque at first. So let's see an example of a hyperbolic group. So we can look at a closed surface of genus at least 2, and its fundamental group. So why is this a hyperbolic group? Well, Riemann uniformization theorem S admits a hyperbolic metric, and its universal cover is the hyperbolic plane. So this fundamental group, pi1 of S, is going to act on the universal cover. The action is properly discontinuous. In fact, to preserves this really nice tessellation of the hyperbolic plane, and the orbit of one of these vertices is just going to track the vertices of the tessellation. And is the action co-compact? Well, what is the quotient? The quotient by the fundamental group is exactly the surface. So this is definitely a co-compact action. So we have our fundamental group acting properly discontinuously, co-compactly. So it's a hyperbolic group. Now, there's another perspective on hyperbolic groups, which comes from thinking of groups themselves as metric spaces. So we have a finitely generated group G. I'm going to fix a finite generating set S. And we want to define some geometry. We're going to do this using the Cayley graph of G. So what are the vertices of this graph? First of all, so the vertices are just the elements of G, and the edges will join the group element G to G times S. So this G is just an arbitrary element of our group, and S is a generator. So we get little edges like this from G to G times S. So edges in this graph just correspond to multiplying by generators on the right. Throughout the talk, whenever we see a graph, we're going to think of it as a metric space where we just endow each edge with length 1. So that makes this graph into a metric space. And we can also define a metric on the group now with respect to S. So this is the word metric. So the word metric distance between G and H will be the distance from G to H in this Cayley graph with respect to S. So to say this another way, what is a geodesic from G to S? Well, so it's some kind of shortest path between G and H. So what does that look like? Well, for each edge, you're just multiplying by a new generator on the right. So what this path is doing is it's telling you a sequence of generators that you need to multiply G by to get H. So the distance from G to H is just the minimum number of generators you need to multiply G by to get H. So what would be an example of a Cayley graph? So let's take a look at the free group on two generators X and Y, and we'll choose S to be this free basis XY. What does a Cayley graph look like? Well, we can imagine building it up by starting at the identity and just kind of moving outwards. So we get edges for each generator. And then there's also, for instance, an edge from X inverse to 1 because you can multiply X inverse by X to get 1. And then you just kind of keep moving out from there. So from X, you could multiply by X to get X squared. You could multiply by Y inverse. You could multiply by Y. Or you could multiply by X inverse, but that just takes you back to the identity. So X will have 4 neighbors like this. And we keep going. So from XY, you could get XY squared, XYX, XY, X inverse, or you could multiply by Y inverse, that takes you back to X, blah, blah, blah. So you just kind of keep going. So it at least looks so far like the Cayley graph is a tree. And in fact, it is. Why is that true? Well, this is basically coming from the fact that the free group doesn't have any relations. So the Cayley graph is not going to have any simple loops. In other words, the only way to get a loop in the Cayley graph is if you multiply by some generator at some point and then multiply by the inverse of that generator to start going backwards the way you came. So the only way to get a loop is if you do backtracking like this. So this tells you there are no simple loops. So this is a tree. Here's another picture of it. So it's just an infinite 4-valent tree. Every vertex has valence 4. Now, this definition of a geometry on G is a little unsatisfying because it depends on this generating set S. We can't really get around that. But actually the metric only depends on the generating set in a certain limited way. So if you have two finite generating sets, S and T for G, then the metrics you get with respect to S and T are what's called quasi-isometric. So quasi-isometry is a weakening of isometry, or it's kind of like a large scale notion of isometry that still preserves many geometric properties that you would care about. So it's kind of good enough for doing a lot of geometry. So what is a quasi-isometry? So you have two metric spaces, X and Y, and then a map between them. And this is what we call a KC quasi-isometric embedding if we have the following. So 1 over K distance from X to Y minus C is at most the distance from f of X to f of Y is at most K dxy plus C. So what am I writing down here? So basically this is saying the distance from f of X to f of Y is the same as the distance from X to Y up to some error. So there's a bounded multiplicative error, that's K, and a bounded additive error, that's C. So these distances agree up to some bounded errors. So that's a quasi-isometric embedding, and it's a quasi-isometry if this map is also coarsely surjective. So that means that everything in Y is some bounded distance from the image of F. So for all Z and Y, there exists an X and X such that the distance from Z to F of X is at most D. Great. So now we can state one of the most important basic tools for doing geometric group theory. This is the Schwarz-Milner lemma, which basically allows you to look at the geometries of certain nicer spaces rather than just the geometries of groups themselves. So the setting is you have G, which acts on a proper geodesic metric space X, and the action is properly discontinuous and co-compact. Then G, first of all, is a finitely generated group, so it has a finite generating set S. And moreover, G with this generating set is actually quasi-isometric to X. So there's a natural map from G to X called the orbit map, where we just fix a base point in X and we send G to G times X. So this map is a quasi-isometry. So word metrics only depend on the generating set, finite generating set, up to quasi-isometry. And this lemma allows us to reduce our word metric to a different nicer space. So for example, if we have one of these surface groups closed, so we have a closed surface of genus at least 2, we saw the fundamental group acts on the hyperbolic plane properly discontinuously, co-compactly. So Schwarz-Milner tells us that the fundamental group is actually quasi-isometric to the hyperbolic plane, which is somehow a nicer space to work with. So what is hyperbolicity good for? Well, it gets us a lot of really nice geometric properties pretty quickly. So first of all, boundaries. So these are kind of analogous to the circle, which forms the boundary of the hyperbolic plane. So you have a proper geodesic metric, proper delta hyperbolic metric space X. And what we want to do is fix a base point in X. And the boundary just consists of all the different ways of going off to infinity in this space. So the space boundary X is the space of geodesic rays based at X. Now, there's a slight technical issue, which is that geodesic rays based at X can potentially stay at finite distance for all time, bounded distance. If that happens, we want to consider the two rays to be the same. So really, this is a space of geodesic rays up to equivalence, but I'm not going to state the technical definition right now. So we could see some boundaries and some of our favorite examples of hyperbolic spaces like this free group. So here the boundary is a Cantor set. Why is it a Cantor set? Well, we can just kind of look at this definition. So what are the geodesic rays emanating from the identity? Well, there are like 4 different directions you could go. And then when you get to a new vertex, well, there are 3 more directions you can go. You can never turn around and backtrack to where you started. So you just have 3 new options for edges you can traverse each time. So basically you can think of this as you start in some direction and then you have 3 different choices at each step. So you can think of identifying at least, say, this chunk of the boundary with sequences where each entry is just 1, 2, or 3, for instance. That's a description of a Cantor set. So that's the boundary of this free group. What else do we get from hyperbolicity? Well, we can say something about subgroups, for instance. So we get free subgroups pretty quickly, and this is coming from this famous ping pong lemma. So you have a hyperbolic group G and 2 elements, X and Y and G, which are infinite order and which do not commute. Then we're going to raise these elements to certain powers and look at the subgroup that they generate. So we look at, say, the subgroup generated by X to the K and Y to the L. And this turns out to be the free group on these 2 generators, as long as K and L are sufficiently large. And this is called the ping pong lemma for a very specific reason. So your elements X to the K and Y to the L are going to be loxodromic elements. So they preserve 2 lines in your Cayley graph, which have distinct endpoints. And they translate along these lines. And on the boundary, they have some attracting and repelling behavior. So this power X to the K will fix this endpoint and this endpoint, and it moves everything from this endpoint towards the other one. So one endpoint is attracting, the other is repelling. And you can study how this works on the boundary. So in fact, this is going to be a really strong attracting and repelling behavior, strong enough that if you take a little neighborhood of the repelling endpoint and a little neighborhood of the attracting endpoint, everything outside of this little neighborhood of the repelling endpoint gets sucked into this little neighborhood of the attracting endpoint by X to the K. And this allows you to play this game. So you fix some point, say P on the boundary, and you look at some word in these 2 generators, and what happens to P is it just kind of bounces between these 4 different sets. And this will allow you to say that as long as your word doesn't have any trivial cancellation of some generator with its inverse, then P is going to end up in one of these four sets. In particular, P doesn't get mapped to itself. So that tells you nothing in this subgroup, or that this subgroup doesn't have any relations. Okay, so it's hyperbolicity is also great for thinking about groups computationally. So the idea here is to write, in the best possible case at least, some computer program which would tell you anything you want to know about your group. So we'll look at a group G, which I'll assume is hyperbolic, even though you can ask this question for a general finitely generated group. And we'll fix some finite generating set. I'll assume that it's closed under taking inverses. And so the word problem is a basic algorithmic problem you need to solve to do computation in your group. So to ask the following question, so given a word in the generators, so here GI is an element of this generating set for all I. So given a word in the generators is W equal to the identity in G. Okay, so you need to be able to tell when a group element is trivial or non-trivial. So this was studied actually by Dane over 100 years ago, and he says there's an algorithm to solve the word problem in our hyperbolic group. And in fact, this algorithm is really efficient. So the time needed to solve it is linear in the word length n. Okay, so you can write a computer program which will take in some random word in the generators and tell you if it's a trivial group element or not. Okay, and well, Dane didn't actually know what a hyperbolic group was. This was a really long time ago, but basically he gave the idea in certain specific cases, which can be souped up pretty easily to cover a general hyperbolic group. So this theorem can be safely attributed to Dane. The conjugacy problem is a similar problem. So you have two words in the generators. These represent two elements of your group. And what we want to know is, are U and V conjugate in our group G? So again, we're assuming our group G is hyperbolic. Again, since the group is hyperbolic, this problem can be solved by an algorithm. So Gromov gave this algorithm. Epstein and Holt later upgraded it to be very efficient. So there exists an algorithm to solve the conjugacy problem in a hyperbolic group, and the time needed to solve it is linear in the input data, which is n plus b. So you can write a computer program. It will tell you whether U and V are conjugate in some number of steps, which is proportional to n plus p. Finally, the isomorphism problem. So here you have two finitely presented groups, and probably you know from abstract algebra that it's kind of hard to tell what a group is just by staring at its presentation. So the isomorphism problem asks, given these two presentations, are these groups the same? So can you tell from the presentations if G and H are isomorphic. So the answer is yes, you can write an algorithm to tell if these groups are isomorphic if you assume that they're both hyperbolic. So if G and H are hyperbolic. So this is actually a very deep theorem. So Law first proved this when G and H are torsion-free, and Damani and Girodel upgraded this to general hyperbolic groups. Okay, so what other stuff is hyperbolicity good for? Well, tons of stuff. I mean, I could go on about this for a long time. Geometrically, hyperbolic groups have lots of really nice properties. They have exponential growth. So if you look at a ball of radius r in the Cayley graph, and you just look at the number of vertices or the number of group elements inside this ball, as the radius grows, the number of group elements will grow exponentially with the radius. Hyperbolic groups have exponential divergence, which means geodesics that start from the same point and move in different directions diverge exponentially quickly. Random walks converge to points on the boundary. This is due to Kajmanovic. I'm putting random walks in quotation marks because you need to assume something about what type of random walk you have. I don't want to write down the hypotheses right now, but this works in a very general setting, actually. Random groups are hyperbolic. This is due to Gromov. And again, I have to put this in quotation marks because you have to say what type of random group, but there are several different ways to define random groups such that the groups you get are generically hyperbolic. And you can say lots of algebraic stuff. For instance, solvable subgroups of hyperbolic groups are very constrained, namely any solvable subgroup will have a cyclic subgroup of finite index. Okay, but what about non-hyperbolic groups? So there are many groups that people in geometry and topology care about that are not hyperbolic. So I'm going to focus on one prototypical example for the rest of the talk, and maybe at the end just kind of mention some other groups. So here's the prototypical example, which is going to be the mapping class group. So here we're going to look at some surface that's going to be orientable. I'm going to assume that it has finite genus, finitely many punctures, and I'm going to assume that the complexity of the surface is sufficiently high. So 3g minus 3 plus p is greater than 1. So this is actually just ruling out a small number of exceptions, like a torus with 1 puncture or fewer, or a sphere with 4 or fewer punctures. And I don't even need to assume this for everything I'm going to say, but it will be necessary for some statements. So maybe this is our surface, for instance. So this has genus 3 with 3 punctures. So we're going to look at the mapping class group. So this is the group of orientation preserving homeomorphisms of S considered up to isotopy. So we're looking at self-homeomorphisms, but we're allowed to wiggle a homeomorphism a little bit by an isotopy, and we consider those resulting automorphisms to be the same. So what are some examples of mapping classes? So we could, for instance, look at a genus 6 surface. So we could kind of arrange 1 handle in the middle and 5 handles around this handle in the middle. And then we just look at a rotation about this axis in the center. So we just kind of rotate one handle to the next, and so on and so forth. So this is a very nice mapping class, which would be called a finite order mapping class, because if you do this 5 times, you actually end up back at the identity. Another classic example would be Dane twists. So here you're going to fix a simple closed curve. So just an embedding of a circle to your surface, and you're going to define a homeomorphism that kind of twists the surface around the circle. So namely, you take the surface, you take this curve, you cut along it, then you have 2 boundary components, and you have kind of tubes connected to these 2 boundary components. You're going to fix one boundary component and take the other and twist it around by 2 pi, and then glue these 2 tubes back together. That's going to define a homeomorphism of your surface. And we can get a bit of a handle on what this looks like. So if we take this green curve here, for instance, which intersects the blue curve once, this mapping class is going to cause it to twist around the blue curve and then do what it usually does. So this is a Dane twist. It's an example of a reducible mapping class. So reducible basically means the mapping class fixes a curve, so you can try to reduce the mapping class to some lower complexity thing by studying the complement of this curve, basically. Now there's one other type of mapping class that I don't have time to define formally, but I want to mention them because they'll come up in this talk and maybe some other talks in this session. So these are the pseudo-anosovs. These are the most mysterious, complicated, interesting mapping classes. And basically what these are stretching and contracting mapping classes. So what these do is the following. So you can put a Euclidean structure on your surface away from finitely many singularities. And then with respect to this Euclidean structure, you can take like a little Euclidean piece of your surface like this. And what your mapping class is going to do is it's going to stretch it horizontally and contract it vertically. Okay, so those are your 3 different types of mapping classes. And now to start talking about hyperbolic stuff, I just want to note that the mapping class group is almost never hyperbolic itself. So to see this, we could look at Dane twist, for instance. So here are 2 disjoint simple closed curves on a genus 2 surface, and we can look at Dane twists on these 2 curves and the subgroup that these 2 Dane twists generate. Now, these mapping classes are operating on disjoint parts of the surface, so they're actually going to commute. So the group they generate is actually a copy of z squared inside the mapping class group. Now, this tells us the mapping class group is not hyperbolic. Why? Well, if it were hyperbolic, then any solvable subgroup would have a finite index cyclic subgroup. Z squared is solvable, but it doesn't have a finite index cyclic subgroup. So the mapping class group is not hyperbolic. So is all hope lost in trying to study this group? Well, no, definitely not, because there's a really nice, beautiful hyperbolic space that this does act on. So this is called the curve graph of S. And I'll define it in the following way. So the vertices are the isotopy classes of essential simple closed curves on S. So what am I saying here? So what is a simple closed curve? Well, it's just an embedding of the circle into the surface. So if you have a curve on the surface which intersects itself, that's going to be non-simple. So this is an example of a non-simple curve. What is an essential curve? Well, a curve is inessential, not essential, if it bounds either a disk or a punctured disk. So these are inessential curves. So we're just going to look at the simple closed curves, and we're going to throw away the inessential ones. So that's the vertex set. What is the edge set? Well, we're going to have an edge from A to B if A and B have disjoint representatives. So what am I saying here? Remember, A and B are both isotopy classes. So what I'm saying here is there's some curve in A and there's some curve in B, which these two curves are disjoint. So those curves are representatives for A and B, the isotopy classes. Now, as usual, we're going to make this graph into a metric space by giving the edges length 1. And let's take a look at a really small snapshot of a small piece of the curve graph. So here are 4 different vertices of the curve graph. These are essential simple closed curves. And we got 4 vertices like this. What are the edges? Well, blue, you can see, is disjoint from everything. So we have an edge from blue everywhere else. Then if we look at green, for instance, well, it's disjoint from blue and red, but we can't make it disjoint from purple under isotopy. So we have another edge from green to red and no edge to purple. So from red, well, yeah, that's connected to blue and green, not to purple. So this is the subgraph spanned by these 4 vertices. But really, this is just a tiny piece of the curve graph. The curve graph is going to be infinite and infinite diameter. So this is the fundamental theorem of Mazur and Minsky. The curve graph is hyperbolic and its diameter as a metric space is infinite. Great. So we have a hyperbolic metric space, but our group is not hyperbolic, and the action on it is not as nice as we would like. It's not properly discontinuous, for instance. So what is this graph actually useful for? Well, a ton of different stuff. So let me kind of give a survey of some things you can use the curve graph for. So first of all, on the algebraic side, you can study subgroups and normal subgroups. And in particular, you could, for instance, fix an element of the mapping class group and ask about what normal subgroup does it generate? So what is the smallest normal subgroup containing this element? This question was basically wide open for a long time, I think, until Damani, Garadel, and Osen broke some huge ground on this. So you have some mapping class F, which is pseudo-Anosov, so one of these complicated mapping classes. Then you can raise F to a power such that the normal subgroup that it generates is free. So you get many infinite rank free groups by taking normal closures of certain pseudo-Anosovs. This was very recently extended by Clay, Mangahass, and Margalit to cover the case of certain reducible mapping classes as well. So there are some reducible mapping classes which normally generate infinitely generated right-angled Artin groups. So these are groups where the only relations are coming from elements commuting. So you get, for instance, infinite products, infinite free products of direct products of finite of free groups, all kinds of other exotic infinite products. So these can be quite complicated, basically. What about homomorphisms into mapping class groups? Well, Besvina and Fujiwara studied this problem, and they studied this invariant of mapping class groups called bounded cohomology. So this is kind of a technical thing. Definitely not going to have time to define it, but it provides a really strong restriction on homomorphisms into mapping class groups. So for instance, it allowed Besvina and Fujiwara to reprove this Farb-Kajmanovic-Mazur theorem about lattices and Lie groups. So for a long time, mapping class groups have been studied in a way analogous to lattices in higher rank Lie groups. And people have wondered, are they like somehow almost isomorphic to higher rank lattices? Do higher rank lattices embed in mapping class groups in infinite and interesting ways? And Farb, Kajmanovic, and Mazur say no. In fact, for any homomorphism from a higher rank lattice into a mapping class group, we have that the image is finite. So there are no really interesting homomorphisms from higher rank lattices to mapping class groups. I'm putting higher rank lattice in quotation marks here because you have to define what you mean by that. So there are certain hypotheses that I don't have time to state. What about quotients of mapping class groups? So here again, you can say a lot, and I'm gonna kind of introduce this by way of a geometric analogy with hyperbolic manifolds. So Thurston, quite a while ago, was studying finite volume, non-compact hyperbolic three manifolds. So such finite volume hyperbolic three manifolds have cusps. And a cusp of one of these manifolds is always going to be a two-dimensional torus times a line. So that's what's going on here. And you can cook up certain closed manifolds using this finite volume manifold. This is the operation of Dane filling. So what you can do is you can cut the cusp off. When you do that, you get a two-dimensional torus in the boundary of your manifold. And now to create a closed manifold, you can glue on a solid torus to this boundary component. So it turns out there are a lot of different ways to do this because you have to choose some homeomorphism from the boundary of your solid torus to the boundary of your manifold. And in particular, there's a curve on the solid torus which bounds a disk. So you have to decide where this curve is going to go, and that's going to cause some curve on this boundary torus to start bounding a punctured disk when you start bounding a disk rather when you fill in with this solid torus. So you look at this manifold M hat, which is M with this cusp filled by gluing on the solid torus. And what's going on to the fundamental group algebraically? Well, we have this free homotopy class A, and when we glue on the solid torus, we're killing it off because now it bounds a disk. So the fundamental group of M hat is actually the fundamental group of M modulo the normal subgroup generated by A. So these filled manifolds are quotients algebraically. And here's Thurston's fundamental theorem, So the manifold you get is almost always hyperbolic. So M hat is hyperbolic, except for finitely many possible choices of homotopy classes of simple closed curves on the boundary. Great. And in particular, the fundamental group of M hat is going to be a hyperbolic group. So now we want to study quotients of mapping class groups. And to do this, Damani-Guerra-Delanosen introduced a version of Dane filling for the mapping class group. So you can study normal subgroups and quotients by these normal subgroups in a geometric way and say the quotients have really nice controlled properties. Like you can make the quotients hyperbolic, for instance. And this leads to some really interesting theorems. So here's one really interesting corollary due to Damani-Guerra-Delanosen. So for every finitely generated group G, there exists a quotient H of the mapping class group such that G is a subgroup. Sorry, yes, G is a subgroup of H. So, yeah, so this is called SQ universality. Every possible finitely generated group, no matter how crazy, will embed in some quotient of the mapping class group. So it tells you there are a lot of quotients of mapping class groups, and they can get very intense. So what else do we learn about mapping class groups by studying the curve complex or the curve graph? Well, on the geometric side of things, we can say a lot. So abelian subgroups are going to be quasi-isometrically embedded. This is due to Farb, Lubotsky, and Minsky. Mapping class groups have finite asymptotic dimension. This is due to Vestvina, Bromberg, and Fujiwara. So this is some notion of dimension for finitely generated groups. It has some really interesting connections with some conjectures about higher dimensional manifolds. Pretty interesting. And finally, this is maybe one of the crowning jewels about the geometry of mapping class groups. So mapping class groups are quasi-isometrically rigid. This means that the geometry of the mapping class group determines its algebra in some sense. So namely, if you have any group which is quasi-isometric to the mapping class group, then it's nearly the same algebraically. So there's a homomorphism from G into the mapping class group, which has finite kernel and finite index image. So this map is nearly injective and nearly surjective. Okay, so again, geometry determines algebra. Okay, so that's all I want to say about mapping class groups, but just to wrap up, what I really want to advertise is that these same techniques involving the curve graph for the mapping class group extend to a very, very wide range of groups. So I'm going to list a whole bunch of groups, relatively hyperbolic groups, outer automorphism groups of free groups, Arden groups, right-angled Coxeter groups, most three-manifold groups, Croak-Kleiner admissible groups, Cremona groups, big mapping class groups, or mapping class groups of infinite type surfaces, in other words, one relator groups, handle body groups, surface diffeomorphism groups. So these groups don't really form one single coherent class, but the really cool thing is they all have very interesting actions on hyperbolic metric spaces, and these hyperbolic actions allow you to use similar. These hyperbolic metric spaces allow you to study these groups in similar ways to the mapping class group. So I think our speakers will talk about various different groups under this list, possibly some groups outside this list. And all of these groups can be attacked using curve graph-like techniques. Okay, so that's going to be it for today. Thank you.